Okay. Thank you. Thanks, Siva. So in the conventional loss minimization problems, it's just enough to near universally, it's enough to minimize just the sample average. But if you have excess risks, what happens is the excess loss scenarios actually like kind of you see only a few excess loss scenarios in the data or in the samples that you have generated. Right? So here in this part, like you see, you have collected a lot of data, but the excess loss scenarios, which I have highlighted in red, only like kind of like are just a few. So you don't see a lot of data or you don't see a lot of samples. This is the grinding problem. So if you try to draw the histogram of the loss realizations, you will see that only beta fraction of the samples actually contribute to your objective. If your objective is, for example, conditional value at risk, which is just the average of this risk over the largest beta fraction of the scenarios. Right? Conditional value at risk is nothing but basically the average of the excess risk over beta fraction, the largest beta fraction of the scenarios. Right? So if you're interested in these excess risks, you don't see them often. That's the problem. And if you are interested in, for example, 99%, like, like if beta is 1 in 100, then you will need 100 times more samples than what you usually require for optimization. In cyber physical systems, such as like maybe safety in cars or in power operations, what you are interested in risk levels which are 10 power minus 4 or 10 power minus 6 and so on. And if you plug in a 10 power 4 or 10 power minus 6 for beta, this is going to be 1,000,000 times or like tens of thousand times the usual sample requirement. That is the fundamental bottleneck. So in some sense, this universal, whatever our comfort zone, just approximate sample average or do a robust version of that sample average, the near comfort, like we are always comfortable with this, that is not anymore applicable when you are dealing with extreme risks. So just like sample average approximation or empirical risk minimization is just plainly ruled out. So what is the alternative that we have? But like before going, let me just give a sense of like what this means, even in a not so rare problem. So here I'm looking at a tail level of beta is equal to 1 in 40, which is okay. So what has been observed that, like you will need about 14 years of data to perform this risk minimization reasonably. And the perils of just trying to minimize sample average, just naively trying to minimize sample average has been documented so well in the literature. So we don't even consider this. Just trying to minimize sample average here would be naive. And what is the alternative? The usual workflow. First, collect data, estimate formulate a model which is describing the distribution, and then try to kind of estimate the model parameters. In these two steps, you get a measure p hat or distribution p hat, which is describing the data somewhat to the extent that we know. And then we try to solve the downstream optimization problem, which is what I started with. I tried to solve the downstream optimization problem by plugging in this p hat. What I wanted to solve was try to minimize the risk subject to the original distribution P, the unknown distribution P from which the data is generated. But I don't have access to it. All I have is at the moment, my best guess is P hat. So I solve the resulting downstream problem. That's fine. And then we get a decision. If we see that out of sample, the decision is not so good, then what we do is we try to improve it by kind of performing some sophisticated model selection. So what we do is maybe we improve the model, we try to kind of like select a more sophisticated model, or we understand the underlying physics of the problem to generate a better model. So we have to do some sophisticated model selection. So this is what the typical workflow is. Now, when it comes to the tails and extremes, what are the common alternatives that we have got? We could consider, for example, using copulas. Like, copulas are a lot popular in finance as well as in risk management, like actuaries, as well as in like kind of earthquake analysis and so on. People use copulas a lot. The popular ones being Gaussian, T, or Archimedean copulas. Just the names, not important what they are exactly if you haven't heard of them. Or maybe one can consider some elliptical distributions, with Gaussian distribution being the standard one. Or one can use some multivariate regular varying distributions. These are special class of extreme distributions. Or like you have this specific class called extreme value distributions. So all of these are possibilities. We are not going to dwell on them. Okay, that's not our objective. But this is the library of models that we have. And we are largely restricted within this library of models. Okay, now, the data may from one of these models, or it may not be. But we are largely restricted to this or a little more, like a little expanded class. But this is the library we have got. So the tricky part that we are facing is something that we haven't seen, the extreme risks, how they are occurring in data. We haven't seen it so often, but we have to fit it within this library. That makes it like quite hard, right? Like, so it is inevitable that we will kind of be making a mistake, which is the model misspecification. So there is a need. So the first pain point that we kind of have in this workflow is that an incorrect distribution model will affect the downstream optimization. Right? If I had made a wrong choice for the model, it will affect the downstream optimization. So this is the first pain point. So this model selection needs to be done carefully. Okay, the second bottleneck. What is so the first bottleneck is the statistical bottleneck, right? Which is what I highlighted now. You handle model bias. How do you try to handle model bias? Typically, you try to build better models, or you try to use how do you build better models? Just understand the physics of the problem better, the mechanics of the problem better. Or that may not be possible in all instances. Or try to build expressive model classes. Some non-parametric models which try to characterize what the underlying dependence between many shock factors are. Try to learn that. Or inject some conservative bias in the problem. So of all the evils that I can live with, I live with a better evil, right? Like, so when I inject a conservative bias, what it does is like I'm kind of hedging against the uncertainty, against the things that I don't know, and I kind of get better decisions. Certainly, this is a very helpful thing, and there is a long literature. There is a long literature, like rich literature, beautiful literature, which tries to kind of consider the worst case. The worst case, like, so all that I don't know, I kind of like consider as an uncertainty, and I try to do the worst case over all that. So the details are not too important. Or like, we can put special constraints on what we don't know, like something like a convexity type shape constraint, or like some special shape constraints, which kind of like allow us to do this worst case analysis. Regardless of the workflow that we do, there is bias in the problem. There is a model error in the problem, which we have to tackle. That is the first pain point that I wanted to highlight. So the question that we are asking, inspired by this pain point, is that given a distribution model that we have decided to use, can we have an algorithm which can automatically debias the model objective of its non-parametric error? So that is the first question. Okay, so by plugging in a wrong or a slightly incorrect distribution, we are introducing a model error whose nature is non-parametric, right? I don't know what type of error I am committing. So can we remove the bias in the algorithm up to a good extent? That is the first question that we are asking. The second pain point that I would like to highlight is there is this prohibitive computation that is needed when you are talking about extreme events, right? So, okay, I have formulated this problem. I have got this model. So this is the optimization model that I'm going to solve. Great, fantastic. Now, how do I solve it? I don't know the objective in closed form, so I have to use some sampling or simulation-based approximation to kind of like see what that risk measure evaluates to. So what I will do is I'll first draw a lot of samples from my computer from this distribution p hat, approximate this risk measure by the samples. That is the usual Monte Carlo approximation, right? I will have those. But to see these extreme events in the sample, if you're interested in a 1 in 1,000 extreme event, you will need at least 10,000 samples to see it a few times, or a million samples to see it a few times. So what's going to happen is these optimization problems, the resulting optimization problems, are going to involve a lot of samples, maybe a million samples. Think about solving an optimization problem with million samples and so many variables, right? That's going to be difficult. So that's, even if I can kind of like pass this step and go to this step, like this step anyway I have to do. Even if I have a wrong model, I have to do this anyway. So there is this prohibitive computation which I have to deal with. That is the second pain point that I want to highlight. For this, what people do typically is like kind of do some sophisticated variance reduction techniques, such as importance sampling, which we will be talking about, or stratified sampling and control variance. These are just names of various techniques, beautiful techniques, or use something called importance scenario generation, and then, or like kind of some special techniques. But what is common about all of these techniques is they require very careful tailoring of the variance reduction technique. Like, so regardless of the technique that you use, there is no algorithmic procedure. You need an expert sitting there studying the large deviations of the problem, and then trying to understand how these extreme events are happening. And then you need someone like who can come up with an alternate procedure, who can come up with an algorithm. So for every problem, you can basically write a paper. That's how it is, right? Like, so there is actually a long list of literature which tries to use importance sampling and stochastic programming in various contexts, but the ones which tries to kind of use importance sampling or importance scenario generation in optimization With rare events, I have highlighted in blue. Okay. Now, I'm addressing the second pain point now, which is this computational bottleneck. So what are the prominent hurdles and what are the solution approaches? This is the one I think like in the time I'll be able to do justice to. Like, so this hurdle I'll be able to do justice to. The other one I'll just probably just explain what the main results are and leave it at that, like within the time. Okay. So what are the prominent hurdles? So we have two giants, like monumental figures in the area, who have kind of said, like, like how do I go about doing importance sampling? Even if I kind of think about taking two random vectors which are proportional to each other, in large dimensions, they are going to be kind of supported on absolutely different sets. So it's in some sense like incoherent. It's very difficult to kind of like think of using an alternate distribution to kind of like measure performance with my current distribution. So that's the claim that they make for importance sampling. What is importance sampling? Importance sampling is just choose an alternate distribution from which these extreme events are going to be seen more often. If you choose it carefully, you will be fine. But how to choose it is a big question. And it can be quite difficult if you have a lot of variables. That's what they highlight. Okay. So is it all hopeless? Do we all give up? Like, is variance reduction not possible here? Actually, like what we have seen in applied probability and rare events literature is that we have seen that not for optimization, but for estimation of risk, there is a rich literature. There is beautiful literature. Many of them like won prestigious prizes because they show beautiful algorithms. They exhibit beautiful algorithms for tackling these extreme events, even when there are lots of variables. So what they have to do is they have to carefully craft. They have to study how these extreme events are happening. They have to study the large deviations of the problem and carefully craft the importance sampling distribution for it to make it to work. Right? So there are these, like, so what we have is this rich literature. I have illustrated a small section here. What I want you to take back from this slide is just, what we have is each paper or each algorithm will work for a particular setting. If you have portfolio credit risk problem with normal distribution, you can use this algorithm. The same algorithm will not be applicable for this problem. If the distribution changes or if the loss changes, it will not be applicable. You need to come up with a different algorithm, completely different algorithm, right? In what sense these algorithms are good? That's what I'm kind of like saying here. We already saw that, like, if you are doing just naive sample approximations, sample averaging, this is what is going to be the sample requirement. So what these algorithms try to do is they try to slash this down 1 over beta as much as possible. Just try to slash this down as much as possible. What is the best extent I can slash this down? Maybe like I can do it 1 over root beta or 1 over root beta power 1 over 4. All of them might be smaller, but how about I just make it vanishing here? This is the smallest I can make, at least in the exponent. If I look at the logarithm of the sample requirement, this is the smallest I can make, right? So you can think of this in terms of logarithm. This is like polylogarithmic in 1 over beta. Just roughly speaking, you can think of it as polylogarithmic in 1 over beta. So what we are seeking to do is slash this sample requirement from 1 over beta all the way to polylogarithmic in 1 over beta. That will be a huge, that is exponential reduction in sample requirement. That will be a huge gain, right? So this is what these papers are trying to do. But the caveat is these papers work, or these algorithms work, when applied to these special instances. Like, so if you have heavy tail random variables and if you have sums of random variables as your objective, then you can use this. If the setting changes, the algorithm has to change significantly. The same will not work. The same may even backfire. That's the problem we have. Is that okay? This is the prominent challenge we are facing. So why is this happening? Why is this happening? If we want to understand what is the primary challenge here, I'm just showing all of this in 2 dimensions, but you can imagine in what happens in, like, 50 dimensions or 100 dimensions perhaps. Okay, so what I'm showing here is like how these excess losses samples are happening for this loss. The green curves are representing the level curves of the loss. They are capturing how the excess risk. So the level. So when I cross this level, it means I have like I have a lot of loss. So these red dots are capturing actually excess loss samples. What we are seeing is if your distribution X is multivariate normal, and if these are the if this is the loss that you are considering, this piecewise loss is the one you are considering, your excess loss samples are concentrating near the center here. So you should develop an importance sampler which puts a lot of mass in this region. If it puts another region, the algorithm will be gone. It will not work. Now, this is in 2 dimensions. If it is in 50 dimensions, it will be in some esoteric corner. How do I do that? Is not so easy. How to kind of like identify that region and put mass exactly there is not so easy. Now, if I change my distribution, oh my God, it changes. So instead of taking multivariate normal, I just keep the dependence to be Gaussian, but I kind of change the marginals alone. Just I change the marginals from this picture to this picture. I just change the marginals. What happened is the excess loss samples are concentrating in a completely different region, right? So this will be a different part of. Then my algorithm should actually shoot for those places. That's the challenge. The third one, if you see, they are kind of happening here. The concentration is happening here. So my importance sample algorithm should try to actually find the right area and actually concentrate the masses here, the samples here. So the task for kind of like importance sampler is kind of unenviable, right? Like if you're operating in 50 dimensions or 100 dimensions, perhaps, oh, this is going to be like in a high dimensional space, and like kind of to identify the right region where these excess losses are happening is going to be difficult. And that's why such an extensive pipeline of work is needed. So if you see how typical approach in rare events kind of try to solve this problem, what they do is they take a model, which means a model is consisting of two things. One is objective and the other is the distribution. So your model can be described what is sums of random variables or the value of a linear program or value of a mixed integer linear program. That is your objective. What is the distribution driving the uncertainty? That is the distribution component. You have these two, okay? So what an expert does is he first sits down, or he or she first sits down and then propose a good alternate sample distribution family to sample from. How do they do it? They perform large deviations analysis. So they try to understand, mathematically characterize where these excess loss events are happening. They characterize that, and that's the first step. The second step is, okay, I have fixed the family, but now I have to find which distribution from the family should I use. That is going to be identified by setting up an optimization problem. So finding this good importance sampling distribution itself will involve an optimization problem. That, for example, if you have a multivariate normal distribution, it could be a quadratic program, or it could be a quadratic program with some additional huge combinatorial structure, or it could be a mixed integer program. So to identify a good importance sampling distribution for a given objective and for a given distribution itself could involve solving another optimization problem. And then finally you solve the opt, and then like kind of, you obtain samples. Since you have sample from a different distribution, I just cannot use it. What I have to do use it, I have to multiply by the respective likelihood ratio with respect to the whole density to kind of revise so that my estimates are unbiased. So this is the typical workflow. So now you can see why this is so challenging for like kind of having this workout for sophisticated objectives. So what we have seen in rare events largely is like we have seen for sums of random variables and so on, like we have been able to complete this workflow. But if I have something like a value of a linear program as what I am considering for finding how the excess losses happen. So for example, if you're doing power systems, you may have your whatever you are interested in, the performance measure that you are interested in could be written as a value of a linear program or a mixed integer linear program. If you have that with thousands of constraints, if you have that, can you do all of this? No, it's going to be difficult, right? So this is the grinding challenge that we are facing, okay? And on top of it, if you have to integrate it in optimization, okay, if I have to optimize on top of this, here I'm showing the loss for loss level curves for two different coefficients. The first coefficient, this is a simple linear loss. My decision is 0.2, 0.8 here. Here my decision is 0.8, 0.2. I am considering two different linear losses. And what you are seeing is when my coefficients of this loss, which my parameter changes, when my decision parameter changes, where the sampler should actually concentrate also changes. So as I move iteratively in solving an optimization problem, where the sampler should concentrate on also changes. So these are the grinding difficulties that we face. So people have actually like kind of experts have looked at this, and then they have kind of said, in optimization, the main difficulty is even if you have a sampler to begin with, a good sampler family to begin with, what is a good sampler for one decision is often not good for other, which means you have to actually have a seamless procedure for, unless you have a seamless procedure for integrating the samplers with optimization, it may not work out well. Like it will be impractical to solve for every choice of decision to solve another complex optimization problem. That will be impractical. Okay. So in some sense, just to summarize, like, so the prominent hurdles that we face are one, all these beautiful rare events algorithms, simulation algorithms that we have, are applicable only for a smaller library, smaller collection of problems. So for a larger sophisticated set, we just don't know what to do. So there is a universe of large problems which involves optimization objectives or ML. It may involve some sophisticated ML predictors. For all these problems, how do I even kind of operationalize this beautiful idea we have seen in Variance, right? So can we kind of have a sampler which is efficient and also broadly applicable for all these problems? This is the first hurdle that we have. This is the first question that we want to answer. The second is one is like, even if I can do it, how to seamlessly integrate with optimization. Because I highlighted like, when you keep changing like the decision, like, your sampler should also change. So how do you integrate seamlessly? So these are the two hurdles we have in using an importance sampling or importance scenario generation type of idea for optimization. Okay. So what we do in this, the second question I'm going to face is, can we have an algorithm which learns this structure from the problem and adapts itself automatically, adapts its importance sampling distribution automatically to the problem at hand? If it can do that, for every decision, then I am done. Like, so we are just asking the question at a very broad generality. It's not clear even if we can answer this. So this is the second question. So just the two questions in this talk, I just summarize. The first one is, can we have an algorithm which adapts its importance sampling distribution to the objective at hand so that it can be integrated with optimization? So this is addressing the computational bottleneck. The second one is, okay, this is all computationally fine, but statistically, I may have committed a model error at the first place by plugging in a wrong distribution. Can I actually have an algorithm to debias the objective of this error? This is addressing the statistical bottleneck. This is the question I posed earlier. Okay, so these are the two questions I aim to address. The first one I will do in detail because there are nice pictures which can give a good idea of what is happening. The second one, I'll just mention the results, but if you're interested, I'll be happy to kind of like explain it in further detail. Okay. The first, I'm just going to give the main idea which can help us towards solving these two challenges, these two questions that I posed. And what are its implications for resolving the two bottlenecks that I kind of illustrated. Okay. So the key idea is going to come now. Like, so even if you have lost a little bit before, this is okay. Like this here we can catch up. Okay. So this is the place I kind of showed before. You may recall this. This was shown to explain why finding efficient samplers has been hard, because when you change your distribution or when you change your loss, these excess loss samples are concentrating in very different regions, and your sampler has to target that. That was the difficulty. Now, what we are going to use is this startling phenomenon, which has not been so much exploited, which is, if you look at the excess loss, how excess loss happens at a very extreme event, that is mirrored much earlier in the tails. So what I am showing here is these blue samples occur 1,000 times more often than the red samples. Both are tail events, both are extreme events. You can think of this as 1 in 100 even. This is 1 in maybe 10 power 5 even. Like, I'm just giving number. I don't remember exactly what these numbers were, but you can think of this as 1 in 100, and this is 1,000 times rarer. So I'm just plotting the conditional distributions of these excess losses. Okay, so so what you can see is in all these three panels that I'm showing here, all these three figures, how the excess event happens at the extreme 1 in 10 power 5 level is mirrored earlier in the tails too, right? Like how 1 in a million event happens or 1 in a 10,000 event happens can be learned from 1 in 100 or a 1 in 50 event. That is the most important thing. So instead of like kind of having an expert who actually is kind of like trying to crack where the concentration is happening, can we let the sample speak where the concentration is happening? Right? This is the question. So if you see here, it's concentrating in the interior, the same. Here it's concentrating on the axis, the same. Here it's concentrating overall, and it's same. So we need to understand for what class of model this happened. Yes. 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 Of course, I fully agree with you. You can always construct a distribution where this will fail. I will actually like show for what all distributions, what is the characteristic of this. If you see, actually, this is a non-parametric characteristic. Like, so there is no parameter involved in describing this phenomena. So this phenomenon can be crystallized by a non-parametric characteristic, and it will be an expressive class of models, which includes almost all models that we use in risk management. Of course, there will be distributions, which if this phenomenon is not there, we cannot do much. But this is going to kind of, subsume almost all the examples that I showed before. All the examples that have been considered and many, many more. All of that will be subsumed here. Okay, so that's an excellent question. Thank you. So this is actually in answering this question, we have to first understand how general this phenomena is. Does this generalize beyond these simple examples? That we have to first understand, right? So we will do that a little after. But like assume for the moment, take my word for saying that this happens widely. Okay. Yes. Yeah, actually, what you are seeing is an approximate. So memoryless property happens in one dimensions, right? This you can think of as an approximate, not an exact version of memoryless, an approximate version of memoryless, a crude approximation to memoryless happening in different scales, happening in completely different scales. But that is a fair thing to do. Yes, but very approximate. Okay. Okay. So now we have this phenomena. What do we do with it, right? Okay. Usually, what we try to do in kind of developing these samplers is to try to find a good sampler for this instance, a good distribution for this instance, a good importance sampling distribution for this instance. So we try to work out separately. But instead, what we are asking is there one transformation? Is there one magic transformation, which when I apply to these blue samples, can impute the right red samples? So can I impute the right red profile by applying this transformation to the blue profiles? So for all these examples, I'm going to apply that one magic transformation, which gives this phenomena. So just to put it in a caricaturally cartoonish way, I can think of it in the following way, just as a crude approximation to what I'm saying. So you have model 1, which is objective 1 and distribution 1, for which you come up with an importance sampling distribution, which is good. Model 2, importance sampling distribution 2, which is good. Model M, importance sampling M, which is good. Now what I'm asking is, instead of like doing this separately instance by instance, can I have one transformation whose push forward distribution, whose push forward measure? Okay, when I apply to the true distribution, underlying distribution, whose push forward measure actually turns out to be a good distribution to begin with. Okay, so is there a transformation of this type which can impute this right distribution? This is what we are looking at. Okay, so we change the question. So until now, the search has largely been in finding F1, F2, F3 separately. But if you change the question, then there may be the scope for making it easy. Okay, that's what we are going to do. Okay, so now I'll just give so with this, I have introduced the idea. I'll just now tell a brief overview of the results, because I'll be able to do justice only to question 1, but I'll give a brief overview of results for both the questions. Okay. So both the resolutions, both the resolving the computational bottleneck as well as the statistical bottleneck is going to use this key observation that you saw, which is how extreme events happen in extreme levels is mirrored in earlier levels too. That's the observation we are going to use. So what it turns out to be for the computational bottleneck, can we have a sampler which learns where it should concentrate automatically? Yes, a fixed elementary transformation of the samples is sufficient. We will show that. The next is, it is usable for a broad variety of risk management models, even those ones involving black box neural networks, or like if you have a random forest predictor. For all of that, like if you for example have a credit risk model involving all these black box neural networks, still you can use this type of transformation to kind of like compute the objective efficiently. Okay, it is also, you can integrate this seamlessly with optimization. Since it's a black box, it's just a transformation. You just apply a transformation regardless of which decision point you are in. So it has potential to be integrated with optimization problems involving CVAR objectives or chance constraints. Okay, so this is one. For the statistical bottleneck, what we kind of show is that we can construct a new objective, which I call a debiased objective, because it kind of like does not include the model error, at least up to a first order. So this debiased objective can be written as objective with the plug-in p hat. You plug in the p hat and solve the resulting optimization. That objective, the stochastic programming objective, plus a correction term. A correction term. This correction term can be computed beautifully from these blue samples, the less rare blue samples. Okay, so you can add a correction term, And what we can show is this debiased objective has zero sensitivity. So when you change your model, actually the objective has zero sensitivity. The derivative with respect to changes in model will be zero, which means, like, even if you have some, which basically means that the following. So if you have zero sensitivity with respect to perturbations in the model, what it means is if modeller's choice induces a bias of epsilon, the bias in the debiased objective will only be epsilon squared. So without the debiasing, what I'm saying is without the debiasing, let's say the error in the objective was epsilon. This will only be epsilon squared. If epsilon is smaller than 1, then you immediately see that epsilon squared is lesser than epsilon, right? So that's the idea here. So epsilon is already a reasonable number, but the bias can be just automatically, like at no extra effort, like just by adding a correction term, you can get it down to epsilon squared. Okay, so that's because of this debiased objective have this special property that, like, when you kind of move in the model space, the constructed objective is not so sensitive to the model perturbations. And beautifully, what is happening is, like, this objective, if your original objective was convex to begin with, the debiased objective will remain to be convex. It does not destroy the convexity of the objective, which is important for computational considerations. So, and it has been observed that, like, this convexity may not be retained generally when you are using debiasing for these type of problems, or generally for like data-driven optimization problems. The idea of debiasing has been around, like, for about 20 years in semi-parametric statistics, but it's again seeing a lot of resurgence. And we have recently, like, with the emergence of, like, some interesting learning algorithms, we are kind of having new debiasing algorithms which are emerging, and they are kind of finding a lot of applications in causal inference, inferring counterfactuals, and so on. What we are seeing here is, like, in a relatively simple stochastic programming setting, how can I debias the objective? Okay. So debiasing has also been finding applications in OR literature, operations research literature. And there is a beautiful paper recently by Vishal and his co-authors, like, which try to kind of, like, do this debiasing for policy optimization, policy optimization. But the objective which comes out there was not convex. But it's interesting that the convexity is retained in the objective, so everything is fine. Okay. So these are the two resolutions that we give from this simple observation that I showed, which is this, the extreme events, how extreme events happens deep in the tail can be inferred from how it happens earlier in the tail. Yeah. So model is, like, your unknown distribution from which data is generated is what is P, and P hat is, like, so P hat is what you are kind of, no, not the sample. The samples are not useful here. Like, you take a sample and then you kind of fit a model, a Gaussian copula model or a T model. Like, that's how, because we are talking about extreme events, you just don't see enough samples. You have to fit a model. These are scenarios where you have to fit a model. Just data alone will not speak. So your knowledge, your domain knowledge will have to somehow creep in via a model. So that's what is a model. The distribution model is what I mean as a model. So what you are using, let's say you used a Gaussian copula, or let's say you used a T copula, that is your P hat. P is the underlying reality. P hat is your. If you have done a mistake with P hat, if you had done a mistake with assuming a wrong family, that's it. Even if you have infinitely many samples, the error is not going to go down. That's what I mean by bias. Okay, cool. Thank you. Okay. Yeah, what I mentioned is, like, if the modeler's choice induces, if the modeler's choice, like, he was using a P hat and solving the downstream optimization problem, if his answer carried an error of epsilon, the debiased objective will only carry an error, vanishing error. If you see epsilon squared is vanishing relative to epsilon, right? Like, so it will carry only a vanishing error relative to the original one, and convexity is still retained. Okay. Now let me just, like, kind of do justice to question 1 at least, and give a full solution to that. Okay. This is the idea I had mentioned before, which is, like, how extreme events happen later in the tail can be imputed earlier from the tails. How general is this phenomena? That's the question Shiva asked. And what we can show is, as long as your PDF can be written in this form, the logarithm of PDF is like a polynomial, or is like a regularly varying function. Okay. What it means is, like, for example, let me make it simple. If for Gaussian distribution, if you take the logarithm of the PDF, it will be x minus mu transpose sigma inverse x minus mu, which is like a polynomial, which is a quadratic function, right? If you have an exponential, you may have something else here, but it will still be like the logarithm will be like a polynomial. So what this is trying to characterize is like this phi function asymptotically is like a homogeneous function. Just roughly speaking, we can think of this phi as a polynomial, but to be precise, it kind of like behaves similarly. Like, so what it means is a near homogeneity. If I didn't have a limit, if phi of nx divided by phi of n1 is like a function which does not depend on n, that is exact homogeneity. But if I require it only in the limit, that is approximate homogeneity. So this approximate homogeneity is what I mean here. Okay. So many distributions that we use common in practice, like elliptical densities, exponential family, log concave densities, Gaussian copula, T copula, Archimedean copula, all of that we use either with light tail marginals or heavy tail marginals, all of that we use actually can be shown to be satisfying this assumption. This assumption is a non-parametric assumption. This phi star you can think of as the shape of the distribution contours. If you have quadratic, it will be like a quadratic curve, right? Like, so this phi star you can think of as roughly representing the shape of the distribution contours. Okay. So, but this is a this phi star can be anything. This phi star you can think of as a shape function, shape of the distribution can be anything, right? Like, it's a non-parametric thing. So in that sense, there is considerable modeling power here. What it does is it allows this phi star to be anything. So there is considerable modeling power. Only this approximate homogeneity for the logarithm of PDF is what we require. In case if you have heavy tail distributions, all we need is, the same thing happens without the logarithm. Just the distribution itself is like polynomial, or like is like nearly homogeneous. That's all we want. So the same thing with logarithm. If you require this for logarithm of PDF, then it is light tailed. If you don't require it without the logarithm of PDF, then it is heavy tailed. But that's all of them will cover. So this does not include all distributions in the universe, but certainly it includes many most interesting classes that we use commonly in optimization or in risk management. Okay, cool. So what we show is like this buys me a lot, like it gives me a large deviations principle. The large deviation principle itself is not too important, but like this actually here, like in terms of explanation, I'll explain this with figures in the next slide. But this large deviations principle is what it kind of gives us a lot of leverage. So this large deviations principle we kind of established for this family. What it means, I'll explain in the next slide. Okay, so let me just crystallize in the next slides. But let me crystallize the assumptions. The first assumption that we are making is on the distribution, that the logarithm of PDF is like nearly homogeneous. And a standard example to think of is Gaussian. X minus mu transpose sigma inverse X minus mu is nearly homogeneous. It's like a polynomial. For the loss, we similarly require it's like nearly a polynomial. That's all. L of nx by n power rho is like kind of converging to some limiting function L star. But what this again says is, if you look at the levels curves of the loss, they are kind of looking similar to, as I go deeper and deeper in how the level curves of the loss are looking, they are also looking similar. Approximate. All we need is only approximate. If you make it exact requirement, then it will be a very tight requirement, which is not reasonable for applications, but you require it only approximately. Okay, and many examples of losses which satisfy this would be a linear program, objectives in linear program, or mixed integer linear program, or quadratic program. All of these objectives will actually satisfy this this property. Similarly, their optimal values will also satisfy this property. If you are interested in like the probability of an excess loss of an LP value being large, so then even that you can study with this. Their optimal values will also satisfy this. And losses returned in terms of ReLU neural networks, all of them will satisfy this. Okay, this is a reasonably generic assumption. I'm not putting any specific assumption on what this L star should be, these phi stars should be. They are completely non-parametric. So there is considerable expressive power or modeling power. Yes. Yeah. Okay, depends on what you are studying. If you are what we are going to study is going to establish the efficiency that I mentioned, the crude nature of efficiency that I mentioned. So the rate of convergence will not feature. But if you want finite bounds on like how this how the variance of the estimator is looking like in terms of with finite number of samples, or with at a finite tail level, the rates of convergence will start mattering. So you have it. Sorry, he asked before. Yes, sorry, just 1 minute. Yes. I right away give up if you have bounded. We can actually transform the problem in a way that all of this will be satisfied, or I can actually formulate a different assumption for which this will be satisfied. But I haven't done that at all because I precisely don't want to do that for the moment, right? Like I don't want to tailor an effort to kind of like solve a specific problem. I want something which is broadly applicable. You take it and right away use, right? But certainly if you have a specific problem, we can engineer a solution which is geared toward that. But that's what we want to avoid at the moment. What if? So this law, okay. Yes. Yeah, if you have it can become infinity. Like, so, okay, like, so we are looking at excess loss values, right? So it can be minus infinity, right? Infeasibility will be minus infinity in some sense. Like, so what, in that case, like they just will not be considered in the level sets at all. If it is minus infinity, it may not be, right? Like, so infeasibility is not a risk. So, okay, it depends on how you view it, right? Like if you have excess losses being large, like for example, if you fail a contract, if for example some contract like didn't get satisfied and you have to pay a lot of money for that, that is a different problem. There is still a feasible solution, but your losses turned out to be large, quite large, right? Infeasibilities of yes. Infeasibility can happen. I do fully agree. And infeasibility can happen in many problems. What I'm trying to argue that what I consider as risk is opposite in direction to infeasibility. That's what I'm trying to say. If you have minus infinity to your infeasibility, which can result if you are solving supremum of an empty set is minus infinity. So if you are maximizing an objective, minus infinity will be your infeasibility, right? But in that case, my excess losses, what I am kind of like looking at is like kind of in terms of like, you know, the large values is what I'm looking at. Okay. Okay. But infeasibility doesn't often typically arise because of the cost playing any role, right? Like infeasibility occurs only within constraints, like if I understand, right? Like, so maybe not, maybe in a physical system, maybe a different story, but like typically if you have an optimization objective, infeasibility happens only because of constraints, right? Like, so not the cost doesn't even feature. And what I'm trying to argue is like the cost and infeasibility, what I consider as large cost and infeasibility are in opposite directions. I can address that maybe after the seminar ends. Okay. Yeah, I would love to chat too, but they are in opposite directions is what I'm saying. Like, so infeasibility is not even being considered at all in the picture here because like they are in opposite. What I consider as excess is in opposite direction to infeasibility. Okay. Thank you. Yes. Okay. Sure. Okay. Okay, fine. So now with these assumptions, these are the simple assumptions we make. I'm going to like kind of pin down how these excess events are happening. So what are the large deviations characterized by me? I'm going to explain in terms of simple pictures. What it says is, remember loss had this L star, which is a function. Density has the 5 star, which is a function. So how these 5-star level curves, the earliest point at which the 5-star level curves and the earliest point at which the L-star level curves hit, those are the cheapest points by which the excess event is going to happen. What it means is, when I kind of like draw this level curves, this is a large deviations picture. When I draw the level curves, what I get is like the intersection is happening in these two X points. Actually, this is where my excess loss samples will be concentrating roughly. So they will be concentrated around these 2 points. As I go deeper and deeper in the tails, I'll see that like it's singularly concentrating around these 2 points. It becomes more and more singular around these points. Okay, so large deviations would give you this characterization where these excess are happening. Okay, but what is beautiful is this is one excess loss event. If I consider a less rare event, what is going to happen is just I'll get the intersection happening in a similar place, in a similar region, and you see the same thing happening here. This is why the self similarity is happening, right? Like, so the two x's can be mapped to these two x's. They are happening in similar place. If I change the problem, if here the concentration is, the large deviations characterization is saying the concentration is happening on the axis. Similarly, here the concentration is happening on the axis. Right? If I kind of like consider the lower level, then similarly the concentration is happening on the axis. So this is precisely crystallizing why under these assumptions the self-similarity phenomenon actually holds. This picture is crystallizing that. Since these are two homogeneous functions, you have the self-similarity holding. Is okay? Where it intersects in a lower level and where it intersects at a higher level, they all will be related to each other by this simple relationship. Okay? Then the question becomes simple. Can we find a rate point preserving transformation? What I mean is, like, these points are called, these X points are called rate points. Where the concentration, where the large deviations is predicting the concentration will happen, they are called the rate points. So can we kind of find this rate point preserving transformations? When I apply a transformation, it should take a rate point to another rate point. It should take the rate point to the respective rate point. Can we find rate point preserving transformations? That's what the question boils down to. Okay? So this comes from a large deviation characterization. So originally we kind of started with this magic, is there a magic transformation which can do this in the sample space? But beautifully, because of large deviations, it becomes a question simply defined on, you know, sets and points. Like, so if I now, instead of solving the question here, I'm trying to solve the question here. Actually, like, if I look at the problem, what it shows is, like, you know, I need to find a transformation which takes this to this and this to this. Similarly, like this to this and this to this. A transformation of that type can be written down easily from this picture. I'm giving the magic transformation now. It is of the form T of X. I take a sample, I apply this transformation. What it does is it stretches each of the component by a factor S, stretch factor S. S is a stretch factor. It stretches each of the component by a stretch factor S. But it doesn't naively stretch. What it does is it applies a modulating factor on the exponent. And it multiplies each of the points. Like, so this is what is stretching. Without this exponent kappa, this would just be a naive stretching. Just multiply all coordinates. But what this is doing is, this is trying to do something more intelligent. What this is doing is, this is actually, what is this kappa? If you see, it is basically the log, kappa is a vector. Each component is going to be stretched differently. Okay? The ith component of kappa will be large if the xi itself is large. If the xi itself is not large, the ith component will not be large. So what it means is, for this is, here both the components are large. So both of them will be stretched. On the other hand, here, only the x1 component is large, the x2 component is 0, right? It's not large, which means only x1 should be stretched. That's what this precisely does. So the factor kappa modulates how much each component should be stretched based on how large they already are. Okay, so that's why this kappa is important. Okay, but it is this transformation or a transformation like this which can do this job. Actually, we can show that this any transformation which can do this job will have to be of this form. It's a tight characterization. It will have to be of this form. This kappa may have some leeway, but it will have to be of this form. Yes. This kappa does not depend on 5-star L. That's the beauty of it. Like, it's just a black box thing, because it's going to automatically impute all the job 5-star L-star is doing. For different problems, it's going to automatically do it. What I'm asking is, at the end of the day, forget about the 5-star L-star of the problem. Can every potential rate point here be transformed to the respective rate point on the other boundary? That's what we are asking. That's it. Okay. So with this, actually, like, now, like, I kind of presented this as a hypothesis, but actually you can see it working. Like, so when I apply it to the samples, what we are having is, like, when I apply this, these are the less rare samples, these are the more rare samples. And when I apply the transformation, we see that actually they are concentrating in the same region where you want to do. Similarly, here the samples are concentrating on the axis, the blue samples and the red samples. When I apply the transformation, the concentration profiles match. So I cannot keep arguing just by showing pictures. Actually, we show a result which shows that, you know, the theoretically optimal sampler, theoretically what is the best thing that you can construct for the problem, actually, and this transformed samples, they concentrate in the same regions that we can actually characterize. Yes, I'll be done. So, and then we show that you have logarithmic efficiency for this problem, which is what I mentioned, right? Like the gold standard. you want to attain polylogarithmic complexity, and you do have that. Without importance sampling, you will have 1 over beta, order 1 over beta complexity, but on the other hand, you will have only polylogarithmic n 1 over beta as the complexity with this sampler. And when you apply it to kind of like this is just an estimation problem, not an optimization problem. We do see the variance reduction happens by a factor of hundreds to thousands. As your this is a neural network problem with trying to kind of estimate what the this is a neural network model which is trying to estimate a credit default risk, and the default risk, like as the loan default probability kind of is made rare and rare, the performance of the algorithm kind of like becomes better. What we are showing is only the savings. Here the savings is 100. Here the savings is 10,000. So as you become more and more, the effectiveness of the algorithm should increase. And finally, if you are putting it in optimization problems too, here I have a portfolio optimization problem with 15 assets, and what I see is like as the tail level increases, you do see a pronounced increase in the savings. So what I'm showing is here is only the savings here. Here 6 times you have a reduction in complexity. Here you have 25 times the reduction in complexity without importance sampling. Like what happens with and without importance sampling, I am comparing. It's 25 times. Okay. So maybe the other one, I will probably not touch it because we are already there. I have some beautiful pictures there too. I'll be happy to explain offline with you. So what we have showed here, just to summarize, okay, an algorithmic variance reduction technique, which, you know, like I kind of showed this workflow, which is required to get a good sampler. An algorithmic variance reduction technique, which automates this entire workflow, right? All that you can do just by searching for, and instead of searching for an alternate sampling distribution, you instead search for a concentration preserving transformation. If you ask the question the right way, maybe the answer is easy too, right? So in that way, like we have kind of like, you know, like we are just connecting like two completely kind of what has been like two completely different areas in themselves. So in applied probability and rare events, you have had tailored samplers, which are like kind of like, which work for stylized models. On the other hand, here you have like in optimization, you have large models which are solving real problems, but like we don't have importance sampling being able to work there. So we kind of make this connection. This one I'll skip since we haven't covered. Yeah, thank you very much for the opportunity. I'll be very happy to take questions and also explain the other part if you're interested. Yeah, but yeah. Thank you.
So maybe I missed that. So I understood why this Y-star is kind of shape preserving, but I don't understand why L-star the loss needs to be shaped.
That's an assumption I have made too. Like without that assumption, it will not happen. But my claim is that most of the losses that we use in practice share that feature. So this is the assumption I have made on the loss. If you have a linear loss, for example, just to begin with, it will be shape preserving, right? Like if you take the level sets at different levels, all of them will be similar. Okay. If you take more sophisticated ones, they will also be. So if you take value of an LP or MILP, all of them will actually satisfy that. Yeah, the convexity doesn't play a role at all here. It's only like this exact property that I have mentioned. That's all is needed, nothing more. The approximate homogeneity. That's all is needed, nothing more.
No, I was actually thinking that the shape can change a lot. You have not, but this assumption is now.
Okay.
So you explained this automated workflow, so you can do way more general cases. Have you explored these tailored in the importance sampling algorithms? How does your new method compare with them?
Thank you for this excellent question. Of course, they are not going to beat the tailored samplers, but certainly not. We do see that the tailored samplers will be much better, not much better, reasonably better. But what you are getting in turn is generality and the ease to use with optimization. If you have to tailor, you cannot use it in optimization. So that's what you are getting ready to work. So you can use this as a rough cut, just rough cut variance reduction. You just apply and get variance reduction, some variance reduction for free. Some good variance, not some variance. We show that this is logarithmically efficient. So this offers, in some sense, in a crude sense, the best possible variance reduction. Thank you.
Let's thank Dr.
Thank you.